So if you can write a governing differential of the form in this form a n x d raised to n y by dx raised to n plus a1 x dy by dx up to a0x, right, into y. A0x into y is equal to g of x. Okay. So when the governing differential equation is of this form, where in front of y and its derivatives, so this is y and these are the derivatives of y. Okay. So and these are the functions in front of y and its derivatives. So all these functions, they should be pure function of x. Alright, so that is one condition. And second condition, y and its derivatives should be to the first power. Right? Y and its derivatives should be to the first power. And when do you say the equation is non-homogeneous? See, our governing differential equation is mx double dot plus cx dot plus kx is equal to f0 cos omega t. So it is, when the right hand side there is some function, then it is a non-homogeneous governing differential equation. Okay. And what is the homogeneous part of this equation? If I equate the LHS to 0, equal to 0, then this is the homogeneous part. Alright. And the solution of this homogeneous part is called as the complementary function. Okay, the solution of this homogeneous part is called a complementary function. Last time we derived that. Right? And this equation will also have a particular solution. Alright, and the particular solution, we said that xp is equal to sum x cos omega t. Correct? That is what we used for the particular integral. Right? Where x wave is the steady state integral. Steady state amplitude. Right? Any questions? Alright, so let's, there is a small quiz on the screen. I will be sending you the link. Okay, I sent you the link for the quiz, and these are the questions. All right, so answer the question, quiz questions, and submit it.
Sir, the form is closed.
Yes.
Sir, the form is closed ऐसा आ रहा है.
Just a minute. Huh? Okay, it is open now.
So still it is coming closed.
Hello?
Still it is coming closed, the form.
Just refresh it, refresh it.
Oh, sir, still it is close, coming close, sir.
So it's not accepting response. It's good.
Yes, sir, it's coming close.
Hello, there was a loss of net connection. Let me open the form. Just hold on a second. Yeah, can you try it now? Hello,
Yes, sir.
are you able to access it?
Yes.
Yeah, just
Yes, sir.
submit, answer the quiz question and submit it.
So can you share the questions?
Yeah, just a minute. If you have any questions about anything which has been just explained, please ask me. All these things should be clear. What is a linear, non-linear equation, homogeneous, non-homogeneous equation. So submit a quiz. I want to see how much you have followed. Submit it quickly. There is not just a true or false. Don't take so much time. Don't unnecessarily discuss with your fellow students. Otherwise, there is no, you will not learn in that way. Are you done? Can I close the form? Hello.
Yes, sir.
Can I close the form?
Yes, sir.
All right. Only
Sir, 1 minute.
yes, respond quickly. That's it. Only 21 students are responding. No one else is responding. So should I close the form? Okay. Let me check the. Anybody else wants to submit? Okay. So yeah, most of you have got it correct. So it is a this is not the governing differential of this equation of the above system. It needs something on the right hand side. So this is false. What is the frequency of vibration of the mass? Not omega n, it is omega, that is the forcing frequency, and it is a linear second order non-homogeneous governing differential equation. Okay. Alright, so for the undamped part, that is for zeta less than 1, we get a complementary solution, that is the homogeneous part. Alright, and we have already derived a solution for that in the earlier section. So I am using the same thing. So xc, that is a complementary part, is x e raised to minus zeta omega nt cos omega dt minus phi. Okay, and phi is this value. Alright, and amplitude x is x0 square plus x0 dot plus zeta into omega n x0 divided by omega n into square root of 1 minus zeta square. Okay. So this is the amplitude, and the particular solution for particular integral, the particular solution as it is called, and it is also the steady state solution, and that is xp, that is p for particular, into x tilde sign wave cos omega t minus phi. Okay, so here the frequency is omega, and external force is in the is a cosine harmonic force. Okay, and phi tilde is the phase angle between the external force and the system response. Okay, so when the force is applied to the system, immediately the system will not respond, it will take some time to respond. That lag is just nothing but the phase lag, and x wave or x tilde is the steady state amplitude. Okay, now the total response of the system will be particular integral part plus the complementary part. So particular integral is the steady state part, and the complementary function is the transient part. What do you understand by the transient part? So this is the steady state part, the amplitude remain constant. The transient part, the amplitude goes on decreasing. Okay, and the total signal you get is a superimposition of both these signals. Okay. Now this transient part, no, this will die out very quickly. See, dies out very quickly. Right. So for some initial phase of the vibration, there will be this transient part, and after that it will be steady state part. Okay. So we can assume that the response is the steady state part only, and we can neglect this effect of the transient part of the solution. Okay. So instead of so our solution is actually we take it as only as the particular integral, and that is x is equal to x till wave cos omega d omega t, so on and so forth. These are the equation of displacement, velocity and acceleration. Alright, so I put this wave sign to differentiate between this amplitude and the amplitude of the steady state part. I hope you have understood that. Alright, so now since there is only the particular integral part, just for convenience, I am just going to replace this symbol by x. Okay, it should not be confused with the it should not be confused with the steady state amplitude. It is not the sorry, it is not the amplitude of the transient part. Okay. So it is the steady state amplitude. It is just for convenience that we are using this symbol because other again and again I don't want to write the that symbol. Okay. So displacement is x cos omega t minus pi. Velocity is minus x omega, and we can write it in terms of pi by 2. So it is cos omega t minus pi plus pi by 2, and x double dot is cos omega t minus pi plus pi. Okay, and we have already discussed that. So the velocity leads the displacement by pi by 2, and acceleration leads the velocity by pi. Okay, so now what we can do is we can make a vector plot. So so displacement lags velocity x dot by pi by 2, and acceleration x double dot by pi. Right? And substituting the values in the governing differential equation, we get these terms. All right. So this term, first term is the inertia force. All right. Second term is the damping force. And third term is the spring force. Okay. So the all these forces are added, and that is what, and it is equated to the excitation force on the right hand side. Okay. Any questions? So we have decomposed that governing differential equation into three components, that is the inertia force, the damping force and the spring force. Alright, any questions? Hello? Alright, so let's review whatever you have learned so far. So answer the next quiz. Again, it is a true or false quiz. I will send you the link. Alright, so I have sent the link for the part B quiz. So open that quiz and answer the questions and submit it. All of you are able to open the form?
Yes, sir.
Huh? Hello? Form is accessible?
Yes, sir.
Are you done?
Yes, sir.
Can I close the quiz?
No, sir. No, sir.
If you have any questions, please ask. This is a self-evaluatory quiz. No, if you are able to answer these questions, then that means you have understood the whatever has been discussed till this point. All right, done?
No, sir.
Chalo, it is only true or false. If you are not able to answer this quiz, if you are not able to understand what the questions are, that means you have not understood what has been taught so far. I have not taught anything new today. I am just doing a sort of recap from what has been taught in the last lecture. So from this slide onwards, we will be starting the new content. All right, I think I should close the quiz now. Okay, I close the quiz. You have already seen the responses. Now let's elaborate on that. So let's first construct the vector diagram for the displacement, velocity, and acceleration. Okay. So let's construct. So you can also construct it along with me. So construct an x-axis, y-axis. So what is the equation of displacement? Yes. Yes, somebody can you tell me? What is the equation of displacement for force vibration?
X cos omega t minus phi.
Huh?
X cos omega t minus phi.
X cos omega t. X is equal to
Minus phi.
x cos omega t minus phi. Right? So, and what is the equation of the excitation force? Alright, there is a spring mass damper system. Mass, there is a spring, and there is a damper. Alright, and to this mass, a force F0 cos omega t is attached. Alright, so F is equal to F0 cos omega t. Alright, so let me first plot the force vector. This is the force vector F0, and it makes an angle of, at time t, it makes an angle of omega t with the horizontal axis. Right? And if I plot the displacement vector, this angle,
Phi.
yeah, correct, it should be phi. Okay. So this is, this total is omega t. So this is phi. Alright. So the lag is the difference between two angles, that is the lag, that is phi. So what does this means? The displacement lags the force by angle phi. Alright. So this angle is omega t minus phi. Correct? Is that clear? Next we will plot the velocity vector. Okay. So how to plot the velocity vector, can anybody tell me?
90° to x.
90° to?
90. It's 90° to x.
To x, to the displacement vector, right?
Yes.
So the velocity vector will be 90° displacement vector. Hello, can you hear me? Hello.
Yes, sir. So voice is very low.
My voice is very low.
Yes, sir.
How about now?
So now
Yes.
No, your voice is low. Okay, cannot be helped, I guess.
You have to cell noise.
Pardon?
There is too much of disturbance.
No, if I use the microphones, no, I cannot hear your voice. That's why. Anyways, let's continue. All right. So the displacement vector. Can you speak a little louder? I cannot hear you. Whatever you are saying. So the velocity vector will be perpendicular to the displacement vector. Okay. So this is the velocity vector. And it has to be perpendicular to the displacement vector. Okay, that we have already derived. Okay. What about the acceleration vector?
opposite to displacement vector.
How much?
Opposite to displacement vector.
Opposite to displacement. So it is angle between displacement and the acceleration vector is 180 degree. Okay, so this is the acceleration. Okay. All right. Now with this, so we have these three forces, right? The inertia force, the damping force, and the spring force. Okay. Now the spring force will be opposite to the displacement. Right? What about the inertia force? Inertia force will be opposite to the acceleration. Whatever direction it is accelerating, inertia tends to oppose it. Okay, so that is opposite to the acceleration. All right. So let me plot those three vectors, and what will be the damping force? Damping force will be opposite to the velocity vector. Okay. So let me just plot these vectors. Three vectors. All right. So this first will plot the inertia vector. So what is the inertia force? M omega square x. All right. So that is the inertia vector. And this, the spring force will be opposite to the displacement. So displacement is in this direction. So spring force will be downwards kx. All right. And what about the damping force? Damping force will be opposite to the velocity vector. So it will be c into omega into x. All right. So this is the inertia force. This is the spring force. And this is the damping force. Okay. Now the spring force vector and the inertia force vector are aligned to each other, but they are in opposite directions. So you can take a resultant of it, and let's assume that the spring force is more than the inertia force. So if I take the resultant of that vector, that will be kx minus m into omega square x. Alright, and perpendicular to that is the damping force. And what will be the resultant of these two?
Excitation force.
Huh?
Excitation force.
Pardon?
Excitation force.
Correct. The applied force, that is F0. Alright. So this is how you plot the vector. So from this, so this is a force polygon. This is what you call as the force polygon. So here you assume that kx is greater than m omega square x. That is the spring force is greater than the damping force. So the excitation force in magnitude is the resultant of this vector and the what is it, the damping force. So this I can express it as in the form of F0 is equal to square root of kx minus m omega square x plus c into omega into x. Alright. So let's take x on one side. So x is equal to f0 divided by square root of k minus m omega square plus c omega whole square. Right. So let's take k outside. This becomes f0 by k divided by square root of 1 minus m omega square divided by k plus c omega by. Now just let's simplify some of these terms. Right, so this is the equation. Right, so let's simplify these equations. So m omega square by k, I can write it as m omega square divided by m omega n square. That is omega by omega n square, that is equal to r square. And c omega by k, c omega m omega n square. Okay, so that is cc into, this is c is equal to cc into zeta, and cc is equal to 2m omega n. Alright, so substitute that, so this becomes 2m omega n zeta into omega divided by m into omega n square. So that is equal to 2 zeta into omega by omega n. Okay, and this term omega by omega n is called as the frequency ratio. Okay? So omega by omega n is r, that is the frequency ratio. Right? So our equation for the steady state amplitude is x is equal to f0 by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Okay. Where the numerator f0 by k represents the deflection under static force f0, and it is this term x0 is equal to f0 by k is also called as zero frequency deflection. Obviously zero frequency because it is under static condition. Okay, so I can write x is equal to x0 divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so that is the equation for steady state amplitude of vibration. Okay, and this quantity x divided by x0 is also called as the magnification factor. Alright, or also called as amplitude ratio. Okay. If I plot these vectors, the kx minus m omega square x, and this another side is c omega of x, this angle is phi, and so tan phi is given as c omega x divided by kx minus m omega square, which simplifies to this form 2 zeta r divided by 1 minus r square. Any questions? Okay, so this is the so both the responses are superimposed and plotted, and f of t, this is the applied force, and the response xp of t is the steady state amplitude, steady state or the particular integral solution. And as you can see, the peak of the response, so when a force is applied, the peak of the response is reached after some angle phi, that is called as the phase lag. Alright, so there is some lag between the applied force and the maximum amplitude that is reached. Right? So I can say that the magnification factor is equal to x by x0 is equal to 1 upon square root of 1 minus r square whole square plus 2 zeta r phi is equal to 0. So magnification factor is x by x0, it is equal to 1 upon 1 minus r square. Okay, for r less than 1. Okay. So suppose for this condition, the response of the system will be xt is equal to x cos omega t, and ft, the applied force is f0 cos omega t. Alright, and if I plot this signal, so what do I get? Okay, so this is the force applied and this is the displacement. Okay, so what do you see from this graphs? When the peak of the applied force is reached, okay, when phase lag is 0, the peak of the displacement is also reached on the same side. Okay, now what will happen when r is greater than 1? Alright, so when r is greater than 1, the denominator becomes negative. Alright, so the response xt is on the other side, so it has to be written in the with a negative sign. It is equal to minus x cos omega t. So it is in the direction of the negative axis. Now when you plot the applied force ft equal to f0 cos omega t, then the graph which you get are in this form, and now the response is said to be out of phase with the excitation force ft is equal to f0 cos omega t. Correct? So earlier case it is in phase, and in this case it is in out of phase. Correct? Any questions? Hello, any questions? Okay, now let's see a typical case when r is equal to 1. So when r is equal to 1 means what? Frequency ratio is 1, that is omega by omega n is equal to 1, or omega is equal to omega n. So when this happens, what is the phenomena? What is this called as?
Resonance.
Huh?
Resonance.
Resonance. When the forcing frequency is equal to the natural frequency, then that phenomenon is called as resonance. Alright. So the natural frequency is equal to the forcing frequency. So magnification factor in this case will become, so in either case, whether it is magnification factor is r square minus 1 or 1 minus r square, especially when there is no damping, zeta is 0. So at r equal to 1, magnification factor goes to infinity. Alright. So if I plot a graph of magnification factor on y-axis and frequency ratio on x-axis, okay. So at r equal to 1, the magnification factor goes to infinity. Okay, this goes to infinity. It is the magnification factor. Alright. So if you see this graph, when r is less than 1, graph is above x-axis, and r is greater than 1, graph is below x-axis. Alright. Now, for the convenience, to study the characteristics of magnification factor versus frequency ratio, what is done? We typically take a mirror image of this graph. Okay, so we plot both the graphs on the same side of the x-axis, and then we study the results. Okay, so let's see that. So this is a mirror image is taken like this, and then we plot the graphs. Alright. So let's study the characteristic features of this graph. Alright, so let's plot. So magnification factor is 1 upon, for zeta is equal to 0, 1 upon 1 minus r square, or it is 1 minus r square root of 1 minus r square whole square plus 2 zeta r whole square, correct? So when this is the frequency ratio r, okay. So when r is equal to 0, magnification factor is how much? Yes, on y-axis I plot the magnification factor. So when r is equal to 0, what is the magnification factor? Hello. Yes, anybody? Put r is equal to 0 in this equation. So how much is the magnification factor?
X naught,
Huh?
x0,
No, see, what is magnification factor? Square root of 1 minus r square whole square plus 2 zeta r 1, right? So magnification factor is, when r is 0, is 1. Okay, so this is 1. Okay. Now when r is equal to 1, so we need some reference axis around which we built these graphs. Okay, when r is equal to 1 and when zeta is 0, okay, when zeta is 0, what is the magnification factor?
infinity.
Infinity. So this graph goes to infinity. Right? And when r tends to infinity, what happens to the magnification factor? It will tend to 0. So all the graphs, as they tend to infinity, they go to 0. Right? And as you start to apply damping to the system, then you will start getting these peaks with the peak value, the maximum, with the peak representing the maximum value of the magnification factor. Alright, and as the r goes to infinity, all these graphs will die out to 0. Alright, and so if this is for zeta is equal to 0, and this is for some zeta equal to 0.3, and so on and so forth. Okay. and these peaks which you observe, they shift to the left hand side. Of magnification factor versus frequency ratio. So one by one we will see the characteristics of these curves. So for an undamped system, that is when zeta is equal to 0, magnification factor tends to infinity as r tends to 1. Okay. Any amount of damping, any small amount of damping, that is zeta is greater than 0, reduces the magnification factor for higher values of frequency ratio R. Okay. At or near resonance. So any small amount of damping you provide to the system, this magnification factor reduces drastically. Okay. That is especially for the higher values of R near the resonance. That is these values. Now for any specified value of R, a higher value of damping ratio reduces the value of magnification factor. Okay. So for any value of R, no matter what is the value of the frequency ratio, if you provide damping, then the damping reduces the value of magnification factor. Okay. Now if zeta 2 is greater than zeta 1, so if you have more damping, then the peak value of magnification factor corresponding to those two will be, so that will, there is a correlation, so MF2 will be less than MF1. So if this is say 1 and this is say 2, so if you see this here zeta is 4 and here zeta is 3 and here the magnification value, the peak factor for zeta is equal to 4 is less than zeta is equal to zeta is equal to 0.4 is less than zeta is equal to 0.8. Right, so these are characteristic features. Right. There are few more important characteristic features. This is an important question from Viva point of view. So there are few more questions that we'll see during the next lecture. Any questions before we end today's lecture? All right, that's all for now. Okay, thank you. Today's practical will be taken by Karthik Sara. A1 batch is the practical today, mechanical vibration.
Yes, sir.
So that will be taken by Karthik sir. And all of you, when you come to the next practical, install MATLAB on your PC. We'll be doing practical on MATLAB next practical.
The student version?
Student version. No, whatever version you have. If you don't, student version is fine. That is good. You can buy that. But at least you can have the. If you are not ready to buy the student version, then buy the demo version. Not buy. Install the demo version.
So what, which one, 2020 or 2019?
Huh?
Which version, 2019 or 20?
Any version will do. Any version will do, because we are going to do some basic scripting and then simulating. So these two, what you say, two toolboxes should be there. Simulating should be there, and basic stuff is already there by default. All right.
Okay.
Okay, sir.
Okay. That's all for today.